Hello and welcome back, it's Michael again. In this video we will have a closer look on the R package Monte Carlo and its functions. The Monte Carlo package provides tools to create simulation studies quickly and easily. It further allows to summarize the results in LaTeX tables to directly include them in a paper or presentation. We will apply this package by doing an example to make it easy to understand what the functions are really doing. The main function of this package is the Monte Carlo function. It runs a simulation study for a user-defined test function and parameter grid. We therefore have to define our own test function in which we have to generate data and apply the method of interest. The second input parameter is the number of Monte Carlo iterations that should be run for each parameter constellation. The possible parameter constellations are to be defined in a parameter grid. For a better visualization, we will show the Monte Carlo function with an example. We want to evaluate the performance of a standard two-sided t-test with null hypothesis that the mean equals to 0. We want to examine the size and the power of the test for changes in the sample size, the true mean of the data, and the true standard deviation. Remember, the power of a test is the chance that the test will reject a false null hypothesis, hence the chance of rejecting H0 when H1 is true. The size of a test is the chance that the test will falsely reject the null, hence the chance of a type 1 error. This means the chance of rejecting H0 while it is actually true. So let's have a look how we implement this in R using the Monte Carlo package. The first thing we have to do is to install and load the package, which I already did before. Then we need to set a seed such that we can recreate our results with the same random numbers. Next, we define our test function that generates data and conducts the t-test for this data. The result of this function should be a decision, 0 if we should follow the null hypothesis, or 1 if we should reject it. The function has three input parameters, n, log, and scale, where n is the sample size, log the true mean of the data, and scale the true standard deviation of the data. These will be the parameters we want to vary and see the effects of these changes on the test performance. In the function itself, we first need to generate data. We draw n random numbers from a normal distribution with mean log and standard deviation scale. We then can calculate the test statistic, which is the mean of our sample divided by the sample deviation and multiply with the square root of the sample size. After that, we make the decision based on a confidence level of 5%, which means we reject the null if the absolute value of the test statistics is greater than 1.96. We then return the decision for this particular sample. The Monte Carlo function requires this result to be a list object. After that, we define our parameter grid, which contains all parameter values for which the test function should be evaluated. We therefore define vectors that contain the values for each parameter separately. We are interested in what happens for different sample sizes, 50, 100, 250, and 500. Different true means. We here take all values between 0 and 1 in a step size of 0.2, and two different standard deviations, 1 and 2. We collect all of these parameters in a list object again. Now we are ready to run this Monte Carlo function. We run it using our test function and the parameter grid as input parameters, and we set the number of Monte Carlo iterations to nrep equals 1000. We save the results in the variable res. So let's run it. We see that it takes a bit and that we are evaluating 48 parameters, which is 4 different sample sizes, 6 different means, and 2 standard deviations. We can have a look at the output object of this function with the summary function. It basically tells us what we just did, so which test function we used and which parameter grid. Further, it tells us some meta information about the simulation, like the required time and the number of used CPUs. The most important thing is the output array, which contains the results of the test function, which means the decisions. down here. With the str function, we can additionally display the internal structure of this object. As we can't really display a four-dimensional array and we still don't have the Monte Carlo estimates, we need to work further on here. So just right now in the array only contains the decisions, which means it only contains the raw data. We would need to calculate the mean for each parameter constellation. For convenience, we don't do this by hand and rather use the second main function of the Monte Carlo package. The makeTable function summarizes the results from a Monte Carlo output in a reasonable way. It calculates the Monte Carlo estimates and stacks the submatrices collected in the array, the rows and columns of a new and larger matrix. It then returns the LaTeX code to include it in a paper or Beamer presentation. As input parameters, the makeTable function needs a Monte Carlo output and information about which parameters to use as rows and columns. We first define the rows of our output matrix. We want a new row for each of the 4 different sample sizes. We have to give vectors of the names of the parameters as input parameters for the function. For the columns, we want the remaining 2 parameters. We should include them in the order in which they should appear in the table, sorted from the inside to the outside. This becomes more clear when we look at the final matrix afterwards. For now, we want the parameter location inside. We further determine that the values in the new matrix should be rounded to 2 digits. We see that we get a LaTeX code as output in the console, which we can copy and paste to a LaTeX document. We see that the makeTable function directly calculated the Monte Carlo estimates by taking the mean over 1000 iterations for each parameter constellation. We further see that we have different rows for each sample size and we have 2 big columns on the outside for the different scale parameters. And for each of those columns we have 6 columns on the inside for the location parameters. The Monte Carlo estimate gives the relative frequency how often the null hypothesis was rejected for each parameter constellation. So if the true mean, the location, equals to 0, the Monte Carlo estimator is an estimate for the size of the test, and if the true mean is not equals to 0, it is an estimate for the power of the test. There are a few more optional input parameters for the Monte Carlo function that could be useful. If we set raw equals false, then the Monte Carlo estimates will be directly saved in the output object instead of the raw data. For a small parameter grid, the results can then be directly seen in the R console, which might be helpful. If we set time end test equals true, the required time for the simulation will be estimated based on a reduced grid and less repetitions. This might be helpful for large simulations or slow test functions. With saveRes equals true, we can save the results of this test run I just mentioned. For big problems, it could be useful to have a look at preliminary results and stop the main simulation if something doesn't work correctly in the code. If we set n CPUs to an integer higher than 1, then the simulation is conducted on multiple CPUs if possible. This can speed up big problems. We will quickly show the raw data option as well as the parallelization on our small example. We use the same seed such that we can compare our results to the simulation before and let the Monte Carlo function run with the same test function and parameter grid, but with raw equals false back there. We see that we now directly get the Monte Carlo estimates in the console, which are the same as in the LaTeX table seen before. Now we try to let the simulation run on 2 CPUs and see what happens. It obviously takes much longer. That's because this problem is too small to benefit from parallelization. It is fast anyway. Here, the computational cost of the overhead that is needed to manage multiple CPUs is higher than the time we can actually save due to the parallelization, so we shouldn't apply it here. But in the end, it still works. We see that the Monte Carlo package can be very useful if we try different parameter sets. We can evaluate our test function for many different parameter constellations without too much coding effort. This might be especially helpful for a sensitivity analysis, for example. Further, we can speed up simulations by parallelization if we need to do many iterations or if we work with really slow test functions. But we also have to mention that it's not always necessary and helpful to work with the Monte Carlo package. Sometimes it's faster and especially easier to understand for another person if we code the Monte Carlo simulation by hand. In the application example about pricing European call options, there wouldn't have been an advantage in using the Monte Carlo package, and it was easier to understand the self-made simulation. However, if we would need to calculate the price for many different options on many different stocks, which means we have different parameter values for the strike price, the time to maturity, the current stock price, and the volatility, or if we would like to make a scenario analysis, what would happen if the risk-free rate changes, then it might be helpful to use the Monte Carlo package. Congratulations! You have now completed our video series about Monte Carlo methods. Thanks a lot for watching. I hope you enjoyed the series and could learn something from these videos.